All right, second last law is, now it depends upon who you hear say this, how you say this. I've always said Guy Lussac. I've heard Gay Lussac. I'm not too sure what the correct pronunciation is. But in 1809, somebody decided to investigate the relationship between pressure and temperature. Now, again, if you are going to monitor two variables, you have to keep the other two constant. So the other two are going to be number of moles. So we're not going to let any gas enter or leave. And the volume stay the same. Now, to keep the volume staying the same, we need to use a rigid container. Now, we've actually already explored Guy Lussac's law using the crushed can example, but I found another example too that I was like, oh, this is actually kind of cool. And it's called the egg in a bottle example. So I'm going to let this video play.
Gay-Lussac's law states that pressure and temperature are directly related. Basically, what this means is that as the temperature in Kelvin increases or decreases, the pressure, which is measured in kilopascals, atmospheres, millimeters of mercury, or torr, increases or decreases as well. As the burning matches are dropped into the bottle and then covered with the egg, they are heating the gas inside the bottle, and so the pressure is also high. When they burn out, the air inside the bottle cools. As the temperature decreases, the pressure decreases too. Consequently, the air pressure on the egg from outside of the bottle becomes greater, forcing the egg through the mouth of the bottle and equalizing the pressure. This is Gay-Lussac's law in action.
So I thought that was kind of cool if you ever want to show a party trick. I don't know how you'd get the egg back out though. I feel like you'd have to just shake the bottle really hard till it breaks up. But the idea behind this law is that when the temperature increases, the kinetic energy inside, so the energy of the molecules inside, also increases. And then that means that the number of collisions against the sides of the container are going to increase as well. And your pressure is going to increase. So really the moral of the story is that when temperature increases, pressure increases as well. And then the idea was that when the candle was in there, you were heating the molecules of air. And then we made it a fixed size container because you put the egg on top, trapping all that air inside. Because the air was trapped inside, it didn't have oxygen to fuel the fire, so the temperature decreased, which meant the kinetic energy of the molecules inside the container also decreases. So the number of collisions with the walls decreases, meaning that the pressure is going to decrease. So when the temperature decreases, the pressure decreases, and then it sucked that egg inside because it always wants to equalize its temperature. But what this shows us is that pressure is directly proportional to temperature. So we would state that pressure is directly proportional to temperature, which means that P equals KT, or K is equal to P over T. So if we have this constant K, we can say that P1 over T1 equals P2 over T2. Now again, the most important thing is that your temperature has to be in kelvins. The pressure, as long as they're in the same units, is fine. But again, I just find that if I put everything in atmospheres, I don't have to worry about that at any point in time. Let's do a calculation. So a gas has a P1 of 836 millimeters of mercury at 20 degrees Celsius. What is the pressure in atmospheres when the temperature is 100 degrees Celsius? So we need to do a little bit of converting here. So we're going to convert our millimeters of mercury into atmospheres because I wanted the answer in atmospheres anyway. So I'm going to convert from millimeters of mercury to atmospheres, where 1 atmosphere is equal to 760 millimeters of mercury. And that's going to give me 836 divided by 760, 1.10 atmospheres. Then I also have to convert both of my temperatures into kelvins. I find this the worst. I'm like, really, every time? So that's going to give me 293.15, but of course I need to keep track of sig figs. This was precise to the tens, so this is going to be 2 sig figs. And then same thing with this temperature. I'm going to do 100 plus 273.15. which is going to give me 373.15 kelvins. But because this temperature is accurate or precise to the hundredths, this is only 1 sig fig. So then to set up my calculation, I have P1 over T1 is equal to P2 over T2, and I'm solving for P2. So again, feel free to put your numbers in right now, or you just simply have to multiply both sides by T2, and you end up with P2 is equal to P1 T2 over T1. I don't know, it feels so silly every time I say it. Okay, so in for P1, I'm going to put 1.10. In for T2, I'm going to put 373.15, which is only 1 sig fig. And then in for T1, I'm going to put 293.15, which is 2 sig figs. So then I'm going to do the calculation. I've got 1.1 times 373.15 divided by 293.15, which is going to give me 1.40, but of course I'm supposed to answer to 1 sig fig, which just feels wrong, but that's okay. I'm going to say 1 atmosphere of pressure, aka it's at sea level. Awesome. Okay, so that is, I believe, the end of Guy Lussac's law.